We started talking about elimination reactions in a previous chapter, but now we're going to see them in more detail. What happens in an elimination reaction is that two groups are going to leave. So this group right here and that group right there are going to leave because a base will come and get the hydrogen, and then these two groups will leave and form a pi bond. So that's the overall reaction that happens. And how does that happen? Well, we're going to have a base. So in this case, we have terbutoxide. You're going to see it like that. That's potassium terbutoxide, which is exactly the same that you're seeing here. Or you may have seen it drawn like, and then the potassium is the counter ion, right? So these are three different ways of seeing potassium terbutoxide. What's the issue with potassium terbutoxide? Potassium terbutoxide is a great base, but it's a really bad nucleophile. It's a bad nucleophile because it's big and it cannot reach to the electrophile, but as a base is great because it has electron density, and on top of it, those alkyl groups, they are donating more electron density to the molecule that is already electron dense because it has a negative charge. So that makes this oxygen very reactive, and because it's a base is always going to go and get the hydrogen. Then the electrons will go to the double bond, and because that double bond, the electrons will go here to form a double bond. That's what I meant to say. And then because we have a carbon right there that is already saturated, it already has four atoms connected to it. Something has to go. And in this case, you already know that Br is a really good leaving group. So that will leave and that will form a double bond. And then it will give us the base that it's no longer the base. Now it's the conjugate acid of the base. And now we have the Br that left, and the potassium is there just as a counter ion for the Br minus. Let's look at another example. So now we have that base. So that base is, so it comes from ethanol, sorry. So that base will come, get the hydrogen, those electrons will go there to form the double bond, and because that carbon right there is already saturated, the Cl will leave. It's a good leaving group, and that will give us the double bond. It will give us the conjugate acid of the base, and it will give us the Cl minus with the counter ion that comes from here. Okay, I hope that makes sense. So what happens in this overall reaction? It's what it's called a dehydrohalogenation. What it means is that you lost one hydrogen and one halogen at the same time, and then that will form a pi bond. So how does that happen? Well, we need to identify the carbons in our substrate, in our alkyl halide. So we have the carbon right there that it's connected to the halogen that we know it will leave. The carbon that's connected right next to the halogen, not next to, but that is connected to the halogen, that is what we're going to call the alpha carbon. Then from there, we're going to count all the other carbons following the Greek alphabet. So we're going to say the next one is going to be beta, but this is also going to be a beta. And then the next one is going to be delta, and so on. So here we have the base that will get the hydrogen, and then the hydrogen electrons will go here to form the double bond, and because that carbon is already saturated, then that will leave. And when that leaves, we get the double bond, we get the conjugate acid of the base, and then we have the leaving group, and we usually have the counter ion right there. So here you have some of the most common bases for dehydrohalogenation. So you've already seen the OH minus. That's a really good one. The potassium hydroxide is another source of OH minus. Then we have sodium methoxide. We'll also have sodium ethoxide. So sodium methoxide comes from methanol. Sodium methoxide comes from ethanol. And potassium terbutoxide, that comes from terbutyl, right? So this one right here is the one that we were talking about before. That looks like this. And then this one right here, sodium methoxide, is the one that looks like that, right? Remember, we never show a real bond between those two ions because those are ionic compounds. So all of these molecules right here, they are very good bases. They are ready to go and attack because they have electron density right there on the oxygen, and they are ready to go and attack. And remember what I was saying before about the alkyls? These alkyl groups are electron donating, so they are donating electrons to the molecule that already has electrons on the negative charge. So again, to draw the products of an elimination, you look for the alpha carbon, which is that carbon right next to the Br, which is my halogen that is going to leave. Then you look for the beta carbon. So here we have 1 beta, 2 beta, 3 betas. And then one of the hydrogens that is going to be taken is the ones that are connected to the beta carbon, right? So again, look for the alpha carbon. The alpha carbon is the one that has the halogen. Then look at the carbons that are right next to it. So in this case, we have 3. And the hydrogen that is going to be taken by the base is going to be one of the ones that are right next connected to it. So in this case, my base will come get, for example, this proton right here. Then this will close. So let me just show you. So my base will come, this will collapse, and it will kick out the leaving group. And this is how we form the alkene. Now, here we have an example where my base, that is terbutoxide, the base can now take 2 hydrogens. You see there are 2 types of beta carbons. So there is 1 carbon here and 1 carbon here. So the base could come and get this hydrogen here or this hydrogen here. Depending on which one it takes, it will give me one type of double bond or the other one. So you see this one is an external double bond and this one is an internal double bond, right? So this one here has 1 H, 2 H's, and this one has 3 H's. And if you saw in the previous video, we were talking about which one of these two is more stable, but then we'll talk about this later in some other videos. So if I remove this hydrogen here, what you can try to do is to see how you get this compound, the first one. And if I remove the hydrogen connected to the beta 2, then I will get this double bond right here. You can try to do that at home. So there are 2 types of elimination mechanisms, and this is going to ring a bell because that is exactly what we had for SN1 and SN2. So for elimination, we had E1 and E2. So the E2 mechanism is called bimolecular elimination, and that 2 comes from the same place that the 2 in the SN2 comes from, because that is a bimolecular reaction that it happens in one step. For the E1, the mechanism is called unimolecular elimination. And again, that 1 comes from the same place where the 1 in SN1 comes. That reaction will happen in 2 steps. Now, the E1 and the E2, the difference between those is the reaction happening in 1 step only, or is the reaction going to happen in 2 steps? Like, my leaving group will leave first and then my nucleophile can come and attack. Remember that from SN1? So in elimination is the exact same thing, but now my leaving group can leave first and now my base can come and get the proton and form the double bond. We're gonna see those 2 types of mechanisms, E1 and E2, in the upcoming videos.